Hi, I'm Paul. We're doing Leetcode must-know interview questions, and today's challenge is design, add, and search words data structure, which they're calling a word dictionary. Okay. Um, yeah, this is the last one we did was to design a trie data structure, and really this is a trie data structure, although there's a little bit more to it. So let's read it. It says design a data structure that supports adding new words and finding if a string matches any previously added string. All right, implement the word dictionary class, word dictionary. It's a constructor. We have an add word method, adds a word to the data structure. And we have search word, Boolean, returns true if there is any string in the data structure that matches word, or false otherwise. All right, here's the twist. Word may contain dots, where dots can be matched with any letter. All right, so wildcards. All right, example. The examples work pretty much the way you think that they would work. But here, let's look at an explanation. So we define a word dictionary. We add the word bad, and then dad, and then mad, and then we search for pad, which is not in there. It's false. Return search for bad. That's in there. Search for dot, AD. There's actually multiple matches. That returns true. Search for B dot dot. That would match bad. That returns true. Word length is 1 to 25. Lowercase English letters, at most 2 dots for search queries. And at most 10 to the fourth, what is that? 10,000 calls. All right. So we can do it with a trie, but with the dot, the thing is, if we hit a dot, we can't handle that with just a normal trie. What we're going to have to do with a dot is try every letter that is a child of the current letter and see if we can match something. Now, it's possible because of this that we may need to backtrack. And so a depth first search, we can add a depth first search to it. Let's get the topics here. Okay, trie and depth first search. Right. All right. So usually the main data structure for a depth first search is a stack, but we could use recursive calls and implement a stack that way. In any case, it's similar in a lot of ways to what we did yesterday. So we can probably reuse some of this code. Let's go. This is the solution for yesterday. We had a class called Trie Node, and we still need that. So let's grab that. Go over here and put that in. Word dictionary. Well, again, it needs a root. So we'll do private trie node root. It needs a constructor. And actually, yeah, this constructor will work. Root equals new trie node. Okay. Add word. Okay. The add word is, let me think about it. Let me grab the add word from over here and see what we need to do with it. All right, go back over here and say try node current equals root. Okay, do we want to I'm trying to think here. Word char at. Well, let me think about this for a second. All right, I think this will work as is, although one thing occurs to me here, and that is I've got C minus A in here 3 times. I could do this, int index equals C minus A, put it here, and then we only have to do that subtraction once. Put it here, put it here. All right, I think that should work. Next, we have search. We're searching for a word. All right. Let's see what we did with the last one. Searching for a word. Probably, well, you know what? We're going to need a recursive, call in this to do the depth first search, but probably we can use some of this. So let me grab it. Go back over here, and for the search, what we want to do is, let me think. We did word and root. Let me think about this for a second. All right, I'm gonna paste this in here and just kind of go with it. Oh, wait. You know what? I don't even want to paste it in there. What I want to do is to say return, and then we need the recursive call where we're going to search for the word from some given starting point, which will initially be root. Okay. We're going to do a recursive call for the word starting at root, and then we can say private Boolean search in node. The word is a string, and the root is a trie node. The way we're using it here, let me scoot this over. The way we're using it here, it's only referring to the root on the first call from search. We're going to search for this word starting at the root of the word dictionary. After that, we're going to be searching for words from a node somewhere in the word dictionary. So I don't think it's appropriate to call that variable root. Okay, get that out of there. We don't need that. So let's say we are now going to look at every character in the word. We're searching for a word. We're going to look at it character by character. What if the character is a wildcard? If the character is a wildcard, now we got to do a recursive search. All right, we have to look at every possible path. So let's say for each child of the current node, we're trinode child in node dot children. You didn't see this yesterday, by the way. The way we implement the trie node is there's a 26 element array, and we convert letters to indexes in that array by subtracting the lowercase letter a. So for every node, we can see if a given letter is a child of that node. All right. So for each child node, if the child is not equal to no, that is, if it exists, I mean, we have to look at all. We have to look at all of them. So, first we got to check that it's not null, that letter does exist as a child of this node. And now we'll do the recursive call, which is search in node. We are going to look for word dot. This is going to run too long. Well, maybe I can scoot it over a little bit. Word dot substring I plus 1. That is, we are going to look for the word, everything in the word following the dot, following the wildcard. All right, so we found a character, it's a dot. Could be anything. If we find a character, and if we can find the rest of the word after the dot in or under, I guess I should say, the child node, then we found the word, or we found a word that matches the wildcard definition. Okay. If we can't find anything that matches the rest of the word after the wildcard, then we're returning false. All right. Now, do I want to put an else on this? I mean, it's going to return it is going to return something there. I'm going to put the else. I'm not sure we need that, but I think Java may get confused on, do we have a return for every path? Let me think about this. Yeah, let's try it like that. Else, and let's get the index again. Where did we do that before? All right, let's do that again. Int index. Okay, so we'll say else. So we've got the index. If, and actually this we can still use, I think. If the Are we calling this node now? Yesterday we called it current, but I think now we're going to call it node. If node children index equals null, it's not there. The word is not there. So we'll return false. And we'll go to the next node equals node dot children at index. Move to the next node. Still screwing this up. Actually, that's also the same thing from yesterday, except that now we're calling it node. All right. I need one more bracket here. Okay. If we get all the way through this, now I got to see what, okay, yeah, so we're calling it node now. If we get all the way through this, another thing that I didn't mention today, but I did mention yesterday, is that, oh, wait a second. Are we setting the end of word in the insert? I think so. Let me double check that. Okay, yes, we're setting end of word. Okay, is that there's an end of word indicator in the trie node. And so when we add a word, we set the is end of word indicator in the last letter to true, because a word being in the word dictionary is different than just that sequence of letters being in the dictionary. So we get to the end, but we have to make sure that that is actually a word that we added. So, all right, let's go through this just one more time. The add word is the same as yesterday, where we start at the root and we add letters as needed, one underneath each other. They're all children of the previous letter. And then we set the word the is end of word to true. All right, so that's the insert. Then the search. Search for every character. Did we get a wild card? All right, if we got a wild card, then we're going to go through every child of this node and see if the rest of the word after the wild card exists as a child of the current node. If it doesn't, we will look for the character as a child. If it does not exist, we can't find it. If it does exist, we're going to go to the next node. And finally, at the end, we'll check for is end of word. I feel like that wasn't a great explanation, but another way to think of it is a trie with the addition of wildcards and a depth first search for the wildcard, or to handle the wildcard. All right. Let's run it, see what happens. I see it's an error, but incompatible types, trie node cannot be converted to int. Where am I doing that? Okay, line 44. If child not equal null, oh, wait. Oh, I got the parentheses in the wrong, I need parentheses here. Okay. All right, let's try it one more time. Compile error, and oh, now I have too many parentheses. I had the parentheses in the wrong place. All right, take that off. Let's do it. All right, accepted. This over. Submit. Actually, let me scoot this over as well. Submit. Wow, it's not great. That's not great at all. Okay. 240. Well, I guess it's not terrible because even the best ones are 158. What did we get? 246. So I guess it's not terrible, but it's still bottom third. So, but it still goes in the scorebook as a win. And that is how to design an add and search words data structure, which is basically a trie with wildcards. And I hope you enjoyed it. Please feel free to like, comment, subscribe, and see you next time.